Good morning, everyone.
Good morning, sir.
So, how many of you have gone through the lectures on the YouTube channel? Just raise your hands. Okay. Okay. So, let us just revise a bit. So, we talked about fluids. What is a fluid? We said that anything that moves, anything that continuously deforms. Uh, so, what is the difference between deformation and motion? Deformation involves motion, but it is relative motion. So let's say this is a solid. Yeah, let's say yeah, this is a solid body and it is moving with some velocity. We will not call it a deformation unless there are uh, relative motions within this solid. Relative motion between any 2 points. So let's say these are 2 points and they move relative to each other, then we will call it a deformation inside that solid body. Same with the fluids also. So anything that continuously deforms, that is, it has internal relative motion between the particles, between any 2 points, then we say that it is a fluid. And anything that continuously deforms under a shear force, because under normal forces it will not deform. Okay, it may not deform. Something that is compressible will deform under normal forces also, but it can be an incompressible fluid as well. That is still called a fluid if it deforms under shear forces. Okay, that was the definition of fluid that we saw. And then after that, we saw what are shear stresses. So it is not enough to just talk about forces here. Force is a vector. Okay. So at a point, you have some magnitude of force and a direction of force. So it is not enough to talk about continuous media like fluids or solids. It is enough for points, but it is not enough for continuous media like solids, fluids. So what we needed was uh, another descriptor for the surface on which this force is acting. So if this is a fluid body, and this is the surface on which the force is acting. Okay. To describe this, we used something called tensors. And we represent tensors by double bar above them. Just like forces are represented by single arrow above them, either you can have two arrows to represent two directions or just two bars are enough. Okay. And for 3 dimensions, we said that there are 9 components. Like this: tau yz, zx, zy, and zz. And here we said that the first subscript denotes the direction of the surface. Direction of surface is the normal to the surface. So this is the direction of this surface, the normal to it. And the second subscript is the direction of the force on that surface. So that was tensor, and we will use that later on, maybe not so much, but still the idea should be clear about tensors. Now we also talked about shear stresses and normal stresses in this stress tensor. We said that these diagonal terms, these are normal stresses. Okay. And these off diagonal terms, these are shear stresses, normal and shear. Okay. Yeah. And then in the recorded lecture, if you have gone through that, can somebody tell what was the topic in the recorded lecture? Whoever has gone through it.
So you were talking about density and force per volume.
Yeah. So we talked about some properties of fluids, and also we talked about the shear stress. So just a minute. Okay. Yeah. Let's say this is a surface and there is some fluid layer above it, and on top of that there is a plate, and it is moving with some velocity u. The velocity profile that you will get inside the fluid, this is the fluid inside it. The velocity profile at any cross section, if you take, let's say we take this cross section, you will see the velocity going like this. So at the bottommost surface, the velocity of fluid particles will be same as the bottom solid plate, bottom surface. The velocity of the bottom plate is 0. The velocity of the top plate is capital U. Small u means the velocity in the x direction. So this is the convention that we will use. We will use either ux or just u for denoting the velocity in x direction. And for y direction, either we will use uy or we will use v. Okay. So here we are saying that velocity is linear. This we will derive later on in later classes. So what is happening here, you can notice that the velocity, the fluid particles tends to be attached to the surface they are at. So the bottommost fluid particles are attached to this solid, and the topmost fluid particles are also attached to the solid here, and in between there is some deformation in this fluid domain, continuous deformation. So the topmost fluid particles, their velocity is capital U. The bottommost fluid particles, their velocity is 0, and in between it is linearly varying. Similarly, for a pipe flow, let's say this is a pipe. What happens here is the boundaries, they are stationary, they are not moving. So the fluid velocity at the boundaries is 0. Everywhere it is 0 throughout the circumference, and at the center it should be maximum because there is the least effect of walls there. So it looks like a paraboloid at any cross section that you take. It is maximum at the center and minimum on the walls, that is 0. We talked about density of the fluid. I think all of you know what is density. It is mass per unit volume. So if you consider a fluid and you take a small volume V naught, okay, don't confuse between this vertical velocity V and volume V naught. I will specify where it is volume and where it is velocity. So right now this is volume. Okay, let's say at some point, around some point P, you consider this volume, or let's call this P1. And let's say around some other point P2, you consider another volume, same volume V0, and take the mass of the fluid around point P1, M0 by V0. Okay, that is density. And density at point 2, P2, we are denoting density by rho. So rho 2 is this M0, which can be different. Okay, if the fluid is not homogeneous, if the density varies from point to point, it can happen, divided by the same volume V naught. So densities can vary, but what is this density at a point? We are calling this rho as density at a point in the fluid. We are saying at point P1 it is rho 1, at point P2 it is rho 2. But can the density be defined at each and every point in the fluid? So let us see that. Let's say you know that if you zoom into this region, what you will get at nanometer scale or micrometer scale, you will start seeing the effects of the molecular effects. Okay, let's say this is my volume at nanometer scale. You will see a lot of molecules moving here and there. Okay, if it is a fluid, these molecules will be moving here and there. Some molecules will go away from this volume that we have chosen here, which is fixed in space at point P1. So this center is this point P1. So some molecules will go out of this box of volume V naught. Some molecules will be coming in. So you can see that the density keeps on fluctuating, because at some point of time the mass is m0, at some other point it is m0 plus something or m0 minus something, depending upon whether a molecule has left or entered this volume, right? So if you plot the density, let's say I tell you to plot density at this point P1 with respect to the volume that you choose around that point P1. If you choose a very small volume, it is so small that only one molecule or molecule is bigger than this, let's say. This is the molecule. Sometimes this molecule will completely overlap with this small volume V0. Then what will be your density? I mean, we have not even seen this concept of density for something like this. But whatever is the mass of the molecule, let's say, from this point of view. So mass of one single molecule divided by V0. And if you still decrease this V0, your density will keep on increasing. Okay. When that molecule coincides with this volume V0. But at some other time, this molecule will not be here, it will go away. Suddenly the density will drop to 0 because mass dropped to 0. So we are not plotting with respect to time here, we are just plotting density versus V0. So at the same time, sometimes, so you will have some uncertainty here, right? At some point density will be very high. Let me plot with this blue color. Will be very high, and at other times it will be just 0, right? There is some uncertainty here. As you increase this V0 volume, this uncertainty will reduce, right? As you make it slightly bigger. Some molecules are leaving, but all the times there are some molecules that are inside also. So it is not going to 0. The density, it has some bound. Okay? And you can imagine that this jitter, it will die down after some volume, okay, where it does not matter whether one single molecule leaves or enters the volume V0. So there will be very small jitter here after some, beyond some volume V0, and then you will have a density that is constant. So this limit after which this jitter dies down, that is known as the continuum limit. So this is the point after which you can treat this material as a continuous medium. If you are below this limit, below this volume, then you cannot consider it as a continuous medium. You have to consider it as something made up of discrete particles, discrete molecules, right? How many of you have heard about molecular dynamic simulation or molecular dynamics? Can you raise your hands? Okay. Seems none of you have heard about molecular dynamics. So it is where people solve Newton's equations, that is force equal to mass times acceleration for individual molecules. So let's say two molecules collide with each other. Then what will be the path they follow, and so on. And they do it for a large number of molecules. And then they take the average of those quantities, such as velocity. They take the velocity RMS, or they take the average velocity, to determine the velocity of the entire material, right? This is one way of doing it. What if you want to do this for, let's say, water flowing out of a glass? Okay, there are so many molecules there. Of course, if you solve for the velocity of individual molecules and you take the average of the velocities of the molecules here, you will get a net velocity in this direction. Okay, in that direction. But is it feasible to do this? So let's do some calculation here. Is this all clear, whatever we have talked till now, this continuum limit and this molecular picture of fluids?
Yes, sir.
Okay. If there is any question till now, you can ask. Otherwise, we'll move on. So now what we are talking about is the feasibility of solving for individual particles, solving the Newton's equations for individual molecules, and then deriving the final velocity of the fluid as an average of the velocities of each of those molecules. Can we do this? So let's say a glass of water has a few grams of water. Let's take a few grams. Let's take a little water right now. Let's say specifically 18 grams of water. Now, how many molecules are there? How many molecules of water are there in this much mass of water? Can you please calculate and write it in the chat window? Yeah, please write the number. That is correct. It is 1 mole. How much is 1 mole? How many molecules? Yeah. So that's correct. About 10 to the power 23. That is a very, very large number. Even if I say that we have to solve for 1,000 molecules, that is 10 to the power 3 molecules. We cannot solve it on a paper, of course. Solving the interaction for all the 1,000 molecules is itself very difficult. If we have a computer, we can go up to, let's say, 1,000,000, 1,000,000,000,000 molecules, maybe. But 10 to the power 23 is a very, very huge number. Even if you get the world's fastest computer with the highest memory, we cannot solve for 18 gram of water molecules, all the interactions between them. So it is impossible. Even if you spend generations of people solving it on that computer continuously. So, but still you see fluid dynamic simulations, right? People simulate fluid flows, People solve for fluid flows. We need to solve for fluid flows. 18 grams is a very, very small quantity. People solve it for submarines, flow past submarines, flow in oceans, rivers, all these things. So this is not a feasible approach to solve for individual molecules, to solve their collisions and solve F equal to ma for each one of them. What is the force acting on each one of them, deriving the acceleration, and then from acceleration you can write it as d2x by dt square. Okay, and then integrating this equation for finding the position of the molecule x. That is for every molecule you have to do this. Okay, that is a very, very difficult task. So people do this in molecular dynamics simulations on computers, and they do it for small number of molecules, not such a large number. So in this course, what we'll talk about is continuum limit, when the number of molecules are large enough so that we cannot solve using molecular dynamics. Okay. Only when they are large enough can you consider the fluid to be continuous medium. Otherwise, if you zoom into this volume, you will see molecules flying around. Okay. You cannot consider it to be a continuous medium. So what is so special about continuous medium and continuum assumption that simplifies the problem for us so that we can solve it very easily? So let us take this volume again. Let us take a two-dimensional area right now, a simplification. If it is continuous medium, you can define all the quantities here as continuous functions of space and time. This is x, this is y. At any point, you can say density is a function of x, y, and time. Similarly, you can say velocity is also a function of x, y, and time. Velocity vector, we can say, which includes x velocity as well as y velocity. You can say pressure is a function of x, y, and time, or viscosity is a function of x, y, and time. Any quantity that you have can be expressed as a function of x, y, and time. And what is so special about writing it like a function of x, y, and time? It allows us to differentiate these quantities with respect to x, y, and time. If it is the molecular picture, there you cannot differentiate these quantities for individual molecules, because where there is a molecule, you have some velocity. In the in-between space between the molecules, you don't have any velocity. It is not defined. So you cannot differentiate with respect to space. Okay. So here you can use the differentiation, integration, all these things, because it is a continuous medium. And then using that, we can write equations for the continuous medium, which you can solve on larger scales. You are not restricted to small number of molecules or anything like that. So we will derive those equations later on. But first, just to see how it works, you already have, I think, studied continuity equation in your school, right? Let's say this is a pipe. The area of cross section here is A1, and the velocity perpendicular to this is U1, the average velocity. And here the area is A2 and the velocity is U2. Then there is a relationship between all these quantities a1, u1, a2, u2. Can you write the relationship, the continuity equation, assuming that the density is same throughout the pipe? Yeah. So a1 u1 is equal to a2 u2, and that is basically the mass conservation or volume conservation also if the density is same. So whatever volume is entering through the first cross section has to exit from the second cross section, right? If it is incompressible, if it cannot be compressed. Okay. Now let's say the velocity is different at each point in the cross section itself. Like I showed you earlier, if it is a pipe, the velocity is a paraboloid. In 2D, it is a parabola. And here also like that. Now here you can express velocity as a function of the vertical coordinate. Let's say this coordinate is some eta, and this is some zeta or something, or xi. And the velocity will be a function of this vertical coordinate, u as a function of this zeta. So here you can integrate this velocity and you can find the average velocity, or you can find the total volume flow rate through the first section. So here we have assumed that it is a continuous medium, this fluid. Only then we can integrate in the y direction or in this perpendicular direction to the pipe. So that is the benefit of having this continuous assumption or continuum assumption for the fluid. So we can do all sorts of this integration differentiation on the fluids if we assume it to be a continuous medium. Now that will be more clear when we go ahead. Now again, the concept of stress that we had earlier. Stress is something that acts on a surface. If you have a number of molecules flying here and there, you don't have a concept of stress. Okay, because there is no surface here on which the force is acting. The force is acting on individual molecules. But if you assume the medium to be a continuous medium, then if you have a volume, if you select a volume in that fluid or solid or anything, then you have these surfaces on which you can define the forces. So on this surface you have some forces. Let's say this is a shear force, this is another shear force, this is a normal force, that is a normal force, and so on. So you can write these forces tau, let's say this is xx. Okay, so some equation which relates these forces tau xx with the velocities inside this fluid domain. Or if it is an infinitesimally small region of space and still you assume it to be continuum, then let's say this is velocity u. You can write velocity u in terms of these tau xx, tau xy, and so on. But you cannot do so if you assume everything to be made up of molecules. You have to take the forces on all the individual molecules, sum them up, and only then you can talk about velocity, the average velocity. Okay. Now let us leave all this mathematical part here. We will deal with it later on. We also talked about this property called viscosity. What is viscosity? Maybe you have already learnt about this. If you have a fluid and you can consider it to be made up of multiple layers, okay, which are flowing past each other, and all of them are applying forces on each other. So taking that example of a plate on top, which is moving with velocity u, and the bottom plate is fixed, it has velocity 0. And we also said that the bottom fluid, the fluid that is touching the surface, exactly touching the surface at y equal to 0, that has velocity 0. Okay, this is also known as the no slip condition in fluid mechanics. It means that it doesn't slip. Okay, if you have a fluid and a solid boundary, some interface between a fluid and a solid, then the velocity of the fluid will be same as the velocity of the solid it is touching. That is no slip condition. This has been observed. This cannot be mathematically derived. This has only been observed in experiments. Similarly, at the top plate also, the layer that is exactly touching the top plate, that has no slip condition, so that is moving with velocity capital U. Now the top layer is moving, the bottom layer is not moving. The top layer will try to move the layer adjacent to it, but that will resist. Okay, so there is some friction, you can say. There is some resistance between the two layers. That is known as viscosity. So then the next layer, let's say this, call it as a second layer, although there are infinite layers you can have. So the second layer will apply some force on the third layer. The third layer will apply some force on the fourth layer, and so on until it reaches the last layer. The last layer is stationary. So you can see that there is some force that is acting on all of these layers, because something is moving, something is not moving. Whatever layer is moving is trying to take the next layer with it. And we talked about this origin of viscosity also, that is cohesion between the molecules. That is the molecular origin. Actually, it is made up of molecules, but our hypothesis for solving, for making it simple, is that it is a continuum. Okay, continuum is just an assumption. It makes things simple. In reality, it is made up of molecules. So what is the molecular origin of viscosity? Let's say these are the molecules of the upper layer, and these are the molecules of the lower layer in blue. The upper layer molecules have an average velocity more than the molecules of the lower layer, right? Because the upper layer molecules are in contact with that solid. They also have some adhesion to the solid. So they have higher velocity, higher average velocity, although the velocity is always random, but the average velocity is higher. Okay. And the lower layer molecules have an average velocity that is lower in the forward x direction. Now these top layer molecules, I have exaggerated to make it more clear. These top layer molecules and bottom layer molecules, that is red and blue molecules, have some cohesion force in case of liquids, not in case of all the fluids, but in case of liquids. In case of gas, because of higher intermolecular distances, this cohesion force is not much. So for liquids, this is considerable. So because of this cohesion force between these molecules, the top layer molecules try to pull bottom layer molecules along with them. Okay. Now, if we talk in terms of continuum, what it appears like in terms of layers, this is the top layer, this is the bottom layer. I have given some space between them to show the forces. Now the top layer is applying some force to the bottom layer. Okay. And the bottom layer in turn will apply an equal and opposite force to the top layer, which is happening even in the molecular picture. Top layer molecules are trying to pull the bottom layer molecules. Bottom layer molecules are trying to pull back the top layer molecules. So eventually what you will see is that the top layer molecules velocity will reduce and the bottom layer molecules velocity will increase slightly. Okay. So there is an exchange of momentum between the two layers. So here you can show this as a force in the backward direction for the top layer. Is this clear? If there is any question you can ask right now.
Sir, I
Yeah.
had a doubt, sir. Sir,
Yeah.
when that solid which is on the top of the layer of liquid, it moves with the liquid. So, sir, the molecules in the liquid always sticks to it, sir. I
Yes.
mean, so that layer is all continuously sticking to it. So the molecules will be same throughout its motion.
Yes.
Okay, sir.
Yeah. So here what we were talking about are the layers just below that layer. The solid was somewhere here and there are some molecules here also. There are some molecules that are sticking which have no slip boundary condition, and then there are molecules below that which are moving. Okay. Still there are vibrations in the molecules. They are not completely stationary. Even in solid, there are molecules which are vibrating. Okay. So all of that is happening. And here, these layers that I am showing, these are liquid layers in the continuum sense because we are assuming them to be continuous media, okay, not composed of molecules. Here we are showing the molecular picture. Okay. So this resistance,
Yes, sir.
this force between the two layers, that is called the viscous force, okay, or viscous stress. So you can see that this stress is in is what, like if you write in terms of the tensor, what are the subscripts here for this force? If this is x direction and this is y direction, what should be the subscript? You can write in the chat window. For anyone you can write, for the blue one you can write.
Sir, tau y x.
Yeah, that's correct. Okay. So the normal to this surface is y direction. That's why the first subscript should be y. And the force is acting in the x direction. So the second subscript is x. Tau ix, we can see that this is shear component. But the viscous forces need not be always tangential or shear components. They can be normal also. That we'll see later on. In this example, the viscous stresses are shear stresses. So viscosity generates these shear stresses within the fluid. So within the entire fluid, there are these stresses. You can imagine that the layer below it will also have similar forces. The upper layer tries to pull, and this layer tries to pull it back, and so on till the last layer. That is viscosity. And this tau yx we derived in the last class, I think, that it is proportional to, in this case, du by dy. As you know that velocity is 0 at the bottom plate and maximum at the top plate, capital U. So there is a gradient. What is du by dy? Because u is varying linearly, so it is a constant, right? It is some constant number in this case. So tau ix is proportional to du by dy in this case, and the proportionality constant, that is viscosity. So this mu is viscosity. And this fact that stress is proportional to du by dy, which is also strain rate. We talked about this, I think, in the last class, but I can explain that again. This is strain rate, and both are proportional to each other. This relationship is known as Newton's law of viscosity. Newton ventured into a lot of areas. This is one of the area, fluid mechanics, in which he found some law. So this is known as Newton's law of viscosity. And this is of course not valid for all the fluids. This is valid for simple fluids like water, air. For complicated fluids like cornstarch solution, shampoo, paint, blood, this law is not valid. Tau ix is some other kind of function of du by dy. Those fluids are known as non-Newtonian fluids, like we said in the earlier class, I think. Non-Newtonian fluids, where this law is not valid, and other fluids are Newtonian fluids, water, air, and other simple fluids. Okay. Now, what is strain? Stress and strain you already know for solids, I hope. If you have a bar, just a simple example, some force is acting on it. The area of cross section of the bar is, let's say, A. Stress normal will be, there's only one stress, so I'm not going to write the subscript. The normal component, that is F by A. And let's say the length was L, and the change in length because of this pulling the bar is delta L, then the strain can be written as delta L by L. If you plot a graph between these two, epsilon and tau, you get something like this. The solid breaks there at that cross This is known as the yield strength, tau y. This is known as the ultimate strength, and this is known as the breaking point. Okay. You have seen this plot, I think, for solids in your school also. For solids, there is a finite strain. Epsilon is called strain. There are different kinds of strain, but right now let us just call this strain. If you apply a fixed force, okay, you will have a fixed amount of strain. But in liquids, we saw that if you apply a fixed amount of stress, shear stress, it will not have a fixed strain. It will continue to deform. So the strain will continue to increase for a fixed amount of force. Okay, because it continuously deforms. It doesn't just deform. So in fluids, what is of importance is strain rate. How is strain changing with time? So that is what this du by dy was. So if I have strain rate epsilon dot, of course not for normal stress, that is for shear stress. So in case of fluids, this is the shear stress. Let me call this tau xy to make it more clear. It can be tau yz also, tau zy, all of those things. But right now tau xy for this particular case of fluid between two parallel plates. This looks like a straight line because tau is proportional to du by dy, where du by dy also happens to be the strain rate. We have derived this. I will derive this again if you ask in the next class. Okay. So tau xy versus epsilon dot is this straight line, and this is also for not all the fluids. This is only for Newtonian fluids. For non-Newtonian fluids, it can be anything you can imagine. Okay. And here we have just talked about tau xy versus epsilon dot, but for some fluids, it can also depend on time. This is strain rate, and that can change with time also. So those are different classes of fluids. In this course, we will deal only with Newtonian fluids most of the times, very less often for non-Newtonian. Okay, so that is all for today's class. If there is any question, you can ask.
Sir,
Yes.
yeah, sir, in the lecture video which you sent,
Yeah.
there there was a time where you said that the tau does not have a negative sign, whether it is in forward or in negative in backward direction. So why is it, sir?
Okay. So there is a sign convention for tau that we are going to follow, just like the two layers that I have showed above. Let's say this is a fluid domain and some forces are acting on it. Some plate is pulling this, some plate is pulling it back. Okay. Now let's say we want to find out the stress at a particular point here. To find out that, we have to specify the surface on which we want to calculate the stress. Let us take the horizontal surface like this, which is oriented in the y direction. So the surface normal is y. Now we break this into two, the top layer and the bottom layer. Now the top layer is applying a force on the bottom layer in this direction. The bottom layer is applying a force on the top layer opposite to it, equal and opposite, right? Now you have this as tau yx, that is also tau yx, but in the opposite direction. Now which one do you tell as the stress at this point? Someone asked you the stress at point P1. at this surface whose normal is in the y direction. Now, which one is it? Is it minus tau yx or plus tau yx? Which one do we take? So for convention, what we'll say is we will take the surface that is pointing upwards in the positive y direction. If the force is in the positive x, we will consider that as positive. If it is negative, we will consider that as negative. But if a surface has a normal in the negative y direction, then the force, if it is acting in the negative x, we will consider that as positive. If it is acting in the positive x, we will consider that as negative. So that is the sign convention. It has to be exactly opposite of what we consider for the lower layer. Only then will our answers be consistent. If someone asks the stress at point P1, we will say it is tau yx positive. If our convention is that for positively oriented surfaces, we will consider the force to be positive in positive x, negative in negative x. For negatively oriented surfaces, we will consider this direction to be positive, this direction to be negative. If we take these conventions, then our answer will be consistent, otherwise not. That's why we take either this direction on the negative y plane to be positive, and this direction on the positive y plane to be positive. Both of these are positive. Is that clear?
Yes, sir.
Okay. Any other question? Okay, so we'll stop here. Thank you.
Thank you, sir.